Okay, in this section, I want to show you how to code up and fit neural networks in a very powerful package called TensorFlow. I'm going to do this for two examples. The first is a simple synthetic example that I showed you in the motivating example at the beginning. Then we're going to walk through a slightly more complicated one, which is where we return to the classic MNIST digit classification problem that we saw in the SVM unit. Okay, just as always, we're going to look at the synthetic demo on the collab.research.google.com website. So navigate over to that and then go File and Open. You should get this dialog box as normal. Hit GitHub and put in my GitHub page, which is github.com/Rangan. When you do this, select the intro ML class and scroll down all the way to unit 9. And in unit 9, there'll be two demos. We're going to start with this demo 1 on the synthetic data. So that should open up pretty fast. So let's walk through this. So the first thing we have to do is import TensorFlow. So if you're doing this on Colab, TensorFlow is already installed. But if you're doing this on your home machine, that means you cloned the GitHub repository and then running it on your local machine. You'll have to make sure you install TensorFlow. That's super easy. Just go, you can look it up on the web, and it's very simple right now. Then we're going to import the standard kind of packages, which are NumPy and the plotting. So if you recall, the first thing we do is we generate some synthetic data. I'm not going to go through how I generated it in too much detail. All I'll just say is that I randomly picked points that are uniform and then computed some probability based on how close they were to a circle. So that's the actual way I created it, but that's not that important. And to plot points, it's kind of just as we always plot them. I look at which are the classes which are 0, which points have a label of 0 and 1, and then I plot the 2 points in different colors. And this is the graph that you saw back in the first section. And we see the nature of this synthetic data, that the green samples are here in the middle and the blue samples are around in the edges. And when we look at this data, we can see that this is not linearly classifiable, so we need a more complex classifier. And that's what motivated us to look at a neural network. So to do a neural network, we just have to download a couple of simple classes from the TensorFlow package. So most of the neural network packages that methods that we need are in this sub package Keras. So we can just get these packages here, which I'll walk through and explain in a moment. Now, the first thing you do if you're working on a notebook, and no one actually tells you this, but this is actually very useful, that it's always good to clear the session. And you can do that with this command here. So you import this backend and go k.clear session. If you're doing this in a script, it's not so important. But if you're doing it in a notebook where you keep on rebuilding the model many, many times, it never gets really erased. The old versions of the model don't get erased. So this is good if you can clear the session. All right, so building the neural network is super easy in TensorFlow. Just give it the dimensions. So we have the number of inputs, which is 2. That's what nx is. And we want to have, say, 4 hidden units, if you recall. And we want 1 output unit. So I'm just going to declare a model, sequential, because it's one layer after another. And it has 2 layers. The layers that we're interested in our case are called dense layers, or sometimes called fully connected layers. And the first one has an input of nx, and then it has an output, which is 4 units. And I'm going to put a sigmoid activation. I'm going to give it a name, call it hidden. And similarly for the output, it will have 1 output. Remember, it's 1 output because it's a binary classification problem. And it'll have a sigmoid output because that's how the binary probability works, and I'm going to call it output. All right. So we just build it. That's super easy. And Keras has a nice way to visualize the structure of the model that you created. So it tells you I have these 2 layers, which I've named. And it tells you that the first one has an output shape of 4. And the next one has an output shape of 1. Now note this none. This none is referring to the number of samples in a batch that you would feed this network. So because you can feed it 100 at a time, 200 at a time, as many as you want, it's left as none to sort of indicate that you can use a variable number of samples. Now the parameters in this is very small. There's just 12 in this first layer and 5 in this next layer. So it's only 17. Okay, now we've built it. We're off on our way to train the network, which is also easy. What you do to train the network is you have to give it an optimizer. And as we're going to discuss, what you typically do is some version of stochastic gradient descent. But there are many modified versions which tend to work a little faster than kind of vanilla stochastic gradient descent. This is one that was developed maybe 5-10 years ago. This turned out to be pretty useful in a wide range of applications called Atom, and you give it a learning rate. And sometimes you have to play around with this learning rate. And in fact, I'm going to show you how to play around with that in a little bit. So you tell it the optimizer, and then you compile the model with the optimizer, and you set the loss. And this is important to set correctly because it's a binary classification problem. You give it, say it's binary cross entropy, and the metrics are just going to keep track of we're going to keep track of the accuracy as the optimization progresses. So let's compile that. So now we just we run it and fit it. So the fitting, we give it the training data, X and Y. And I say I want to run it for 10 epochs. Remember, each epoch is I'm running through the whole data once. And I'm running through a batch size of 100 samples. So let's just run that. All right, if I run this, it just does it super quickly. The accuracy is getting a little better, or the loss is going a little bit down. But it's not going down very much. And the reason is that it needs many, many more epochs to run for this case, because the number of elements in a batch is very small. So we need to run it like around at least 1,000, maybe 2,000 epochs, ideally. Now, if I ran it, what will happen is that this printing will just get hideous because it'll have so many outputs. So I need to, there's a couple of different ways around this. So one way to do this is you can put this verbose 0 option in the fitting. And then when you do that, it won't print anything. But I kind of want to still print a little bit once every certain number of iterations. So what I'm going to do is I'm just going to run it for a number of iterations. And in each iteration, I'm going to do some number of epochs, I think let's say about 50, and then print the loss and accuracy every 50 iterations. All right, and I'm going to run it for 20 times 50 of these epochs. So here's my printing. It's still pretty fast, and you can see that the accuracy is getting on the training data is going up and up and up, and it kind of saturates here at about 86% in this case. We could also plot the loss function and the accuracy as a function of the epoch. And you see it started off here, and the loss function went down, and eventually it would have continued to get a little lower, but probably not much lower if I ran it for more. And the accuracy started off at around 67%, and it kind of went up like this. All right, it got to about 86%, and it's kind of saturating at this point. Now, what I showed up there was one way to kind of manually do it, but in a more slightly better way is you could use something called a callback function. So when you have a callback function, it's a function that you give the fit method, and then it will call this function. And in this case, what I'm going to do is when it gets called, it's actually an object itself. So I'm going to call it periodic print loss because it prints the loss periodically, right? And then whenever the steps meet some criteria, I'm just going to tell you which step it's in and what the loss is at that step. And then I'm going to create that callback loss function here with the parameters. And then I'm going to give the fit that loss function as that callback. And I'm also going to suppress the other printing out. So that's just a little more sophisticated way of doing this. Let's run this, all right, and we get a similar output. Now let's take a look at the decision regions. This is more just plotting gymnastics than it is anything else. So I want to plot these decision regions like this. Let me just actually, before I walk through the plot, show you what we want to plot. So we have our inputs x0 and x1. And for each x0, x1 point, I want to plot the probability that my classifier thinks it's a 1 or a 0. So it'll give some plot like this. So let's just run this code. It comes up with a slightly different picture each time because the code, neural networks are trained with some random initial condition and random data, but they all kind of get roughly the same shape. So in this case, we get this shape of this quadrilateral in this case, which you can see kind of defines the locations of these green dots here. Now, the way you create that point is just, as I said, some plotting gymnastics. I create some points between 0 and 1 and use this mesh grid and kind of convert it to an array of with two columns with all the points. And that's what all this gymnastics does. And then I provide that set of all these points, the model, and I predict to get the values of the probabilities, all right? And then I reconvert it back to a grid and then use the im show to make that plot, and then I plot the data on top of it. So that's how that's the little bit of plotting I did to make this little pretty plot. All right. Okay, so that is plotting the final region. You see it kind of works as we expected. I also want to plot the outputs from the hidden layers. So let me just show you what I want to plot. So remember that there are 4 hidden units in this case. So again, for each x and y, I want to plot out what the output of that hidden unit is, which is a value between 0 and 1, to give an idea of what kind of linear regions are being used to build the final region. So to do this, what you do is this other little trick, which is I'm going to get one of the layers from my original model. And then I'm going to make a new model, which will have the same inputs, but it will just have the outputs as that layer. So it kind of slices off just that first layer. And then I can take my same data that I built before, run it through this new model, and then pull out the hidden values. And then all of this is just plotting the outputs and making this subplot picture like that. So let's just run that in this case here. You get different values each time. And you can see the regions. And in this case, you can see that the regions it picks are getting the different edges of that quadrilateral. We can also print the model parameters. There's 2 ways to do this. You can get, for any model, you can just call this get weights function. And what this will do is it will give you a list of weights. So, but that has the weights in all the different layers. So in this case, there are 4 weights in total. So this actually turns out, you have to be careful about figuring out which weights are from which layer. This one is the biases from the hidden layer. This one looks to be the weights in the hidden layer. These are the weights in the second layer, and the biases in the second layer, something like that. All right, a little more easy way to try to figure it out is you can go to each layer, you can grab the layer with this get layer command, and then you could pull out the weights and biases from those layers. So if you run that, it can tell you here what the weights and biases are. All right, that wraps up this little quick demo to show you how to do a neural network on a simple synthetic data example. Okay, now that we've done that synthetic data example, let's go to a slightly more complicated example, which is that classic MNIST digit classification. All right, the MNIST demo can also be loaded up on the colab.research.google.com page, or if you've, again, downloaded or cloned the GitHub repository to your local machine, you can run it there as well. But I'll just use the Colab site. So when you're on the Colab site, navigate over to that demo 2 in Unit 9, and after you pull it up, as before, you'll get this MNIST classification demo. So this is pretty standard. It follows basically the same format that we did for the synthetic data case. First, we load up the TensorFlow package. Again, you have to have that installed if you're running it on your local machine. That'll take it a few seconds. And the first command usually takes a little bit of time on Colab. Then we'll load a couple of standard packages. And if you recall from the SVM example, we can actually get the MNIST data directly from the TensorFlow package. So we just, again, use that mnist.load data command. And those numbers are between 0 and 255, but we want to rescale them so they're between -1 and 1. So that downloads pretty quickly. What actually happens here, because you're running it on this virtual machine, it pulls that data and to that virtual machine and then loads it. All right, let's just look again at the digits and what they look like. This again is code from the SVM unit, so you can go back there and look at it. But just to visualize it, each digit here is a 28 by 28 record, and these are 4 examples for 6, 7, 8, and 6. You can plot more. I just randomly picked 4 of them. All right, let's create the neural network that we want to do to classify the digits. Remember, what the problem is that given a digit, we want to output what that number is. So for example, in this case, we want to show that this is a 6 and this is a 7 and so on. So again, this follows pretty much the same format as a synthetic data case. We first load some methods or classes from TensorFlow. And as always, I just as a matter of practice, clear the session in case there's any other models that have been loaded up previously in the notebook. Then we create the model, and that's super easy. We're going to just, the number of inputs will be the number of the shape of the training samples, which in this case will be 784. We're going to actually pick a fairly large number of hidden units, about 100, or at least large relative to what we did in the simple synthetic case. And the number of output classes will be 10 because there are 10 digits. So then we create our model, which will be sequential as before, because it's one layer after another layer. The first layer will take the input and output the number of hidden units, and I'll have a sigmoid activation. You can play around with different activations if you want. And then because this is a multi-class classification problem, the output activation will be the softmax. All right, so let's run this. And we can print the model summary, and it shows us indeed that we have these 2 layers. And again, remember that this size here is the output size, and there's a none in the first entry because you can have an arbitrary number of input samples when you apply that. So if you apply this, say with 1,000 records into this model, the output shape would be 1,000, 100. But you can apply it with a variable number, so it leaves it as none. Total number of parameters about 79,000, so that's quite a bit more parameters than what we've had in the past. But we'll see if you'll be able to train this without any problem. All right, just as before, we want to select an optimizer. You'll have to play around a little bit with the optimizers. Again, I'm using the same optimizer as in the synthetic data case, but with a slightly smaller learning rate. And then we compile it, giving it the optimizer. You have to pick the loss function correctly. In this case, it is a multi-class classification problem, so we want to use the categorical cross entropy. And then I'm going to also say to keep the track the accuracy of the classifier as we progress. So we just compile it. That's really fast. Then I'm going to do the fitting. I'm going to run it for about 30 epochs and with a batch size of 100. And I'm going to, at the same time, I'm going to have it measure with this validation data here, measure the accuracy of the test data. So let's run that. This will take a little bit of time. So it comes to about maybe the first time about 91. It's already doing pretty well on the test, 95 and so on. So we'll just let this finish. All right, I didn't want to bore you waiting for that to finish, so I just took a little break in the video, but we're done now. It took about 2 seconds per epoch, so it took just about a minute. And you'll see after the 30 epochs, you got an accuracy of about 97%. And you actually did pretty well even after just about 10 epochs. If we want to just plot that history. So when I ran the data, let's go back here, I had the output of the history output. That's useful because that captures the accuracy over the epochs. This is actually a dictionary, and you can get both the training accuracy and the test accuracy. And then let's just plot that over the epoch numbers. And we can see here, this is the blue line, which is the training accuracy, and that's getting close to 1. So it's almost perfectly fitting the data. But the test accuracy goes up and it saturates about 97.5%, which is pretty good. It's not actually as good as what we got with the SVM, but we could actually expand this neural network, and we'll show how to do that and get even higher accuracies. If we want, we can evaluate the accuracy of this model on the final test data, and indeed we get about 97%. Now, one very common feature, just like SVMs, is that we want to save our model in case we want to use it again, because training it can take some time. So Keras actually provides, or TensorFlow provides, some very nice routines for this. We can just save it to a file. So I'm just going to do this, go model save, and it saves it in this file called the H5 format. So just give it that. And then if we want to reload it, I'm going to reload it into another model, call it model 1. I just use this load model command, and it reloads it. And now just to test the accuracy, I'll just do this manually first. I would take the test data, and then it would output the logits of this, and that's what this will do. And then I will go through each column to predict the maximum value. Okay, to see actually what happened here, what I've done in this little bit of code is printed the first 5 rows of Z. So you can see that each row of Z has 10 values, and it has the value summed to 1 with the highest value on the class which it predicts. And then that Y hat is just pick the index of that class. So for example, in this first row here, it's almost 99.9% accurate that it is digit 7. And in this case, for example, the highest value is on column 2, so Y hat is 2, so and so on. So that's all this code did. All right, so we can run that like this. And now to test the accuracy, all I would do is compare the predicted class with the true test class. And when I run this, I get about 97.5%. It might vary again every time you run this code. It might be slightly different because of random initializations and so on. Okay, you can also instead of doing this manually, you can do this with this built-in function called sparse categorical accuracy. You can import that from the Keras metrics. And then what you give it is the true values and the logits, which is Z in this case. And then you could take the accuracy, which is the mean of those values, because it produces one output per sample. And then if we run that, we get here it's about 97.3, which is the same value as what we did manually. All right. That wraps up this MNIST demo, and you've seen how to do a very simple example. You can go on to the lab where you're going to do a similar example with some music classification.